This is on the hydraulic head. This is another set of example where they use a Bernoulli equation based on Darcy as well. So here we use the equation, if you recall the earlier class, HT, the total hydraulic potential of a fluid, equals to HE, which is elevation, HP, which is the pressure head, plus velocity hHV. But for the subsurface flow of liquid, HV is negligible. This one you can assume is very small, you can assume it's 0. So that's why we only use in terms of to calculate the hydraulic head or hydraulic potential or fluid potential, or sometimes even called energy potential of a liquid subsurface, HT is just summation of HP or HE with HP, elevation and pressure head. Okay, example 2. For this question, it asks you to find the total hydraulic head at point A, B, C, D, E, F, and G on the layout as follow. And it is actually to find the total hydraulic head from datum 1. So we're gonna see where is the datum number 1. That's there. That's datum number 1. And the point is A, B, C just outside the media, D within at the center of the media, E just outside the media, F and G. Now, if you can recall how to find the total hydraulic head, HT equals to elevation head plus pressure head. Okay, what we know here, from this equation, we try to find for each of the individual points. As mentioned earlier, elevation head is measured from datum. So if this is the datum here, elevation means it measures from datum. If it's above the datum, the value is gonna be positive. If it's below the datum, the value gonna be negative. In this question, all the points are either on the datum or above the datum. Whereas the pressure head is measured from the water table level downward, because pressure, yeah? So you look at this water table, and then this is 2 water table. So whichever the point, which pressure that they experience down, yeah? Going down, pressure is always from top to down. Right, okay. Where we can actually, let's write a proper, we put it in a proper table. You're gonna find A and so on. And then we found the elevation head first. So remember earlier, elevation is measured from the point of datum. Datum here, datum 1 onward. So we look at A, elevation. You look at the datum 1 goes along here, and then it is actually 0.4 meter from the datum. So for A is 0.4 meter. And then we look at for B, elevation of B, it is fall on the datum. So the elevation is equal to, it's gonna be 0, on the datum point is gonna be 0. C also 0 because it fall, it sit on the datum, no elevation, no reduction in elevation. D is also 0 meter. E is 0 meter. Now, E, F, and G, you might it is sit on this side of, what do you call it? This side of diagram. So for pressure, you gonna calculate based on the water table here. For A, B, and C, the pressure is going to be calculated using water table here. So for elevation is quite simple. It's just a matter of measuring from the datum. They share the same datum regardless where they are positioning. So we continue. The F also sit on the datum, so it is actually 0 elevation height. And then G, if you look at G point here, it is actually above 0.3 meter from the datum 1, so it is 0.3 meter. Okay, next is to find the pressure head. So we're gonna write HP here. Recall earlier, pressure head is measured from the water table level. So here, water table level. So if you look at it, this all 3 point is actually experience pressure from this side of the well, whereas on this side of the well is experienced not from this side of the well, but it experienced this kind of pressure head. The middle part D is experienced, they have some sort of reduction because of you have a media here which is porous, and we're gonna calculate the D point separately, but we can actually solve the one that actually straightforward, point A, B, and C. So for point A, the pressure, because we measured from the water table level, the pressure is sit on the water table level, so the pressure head is equal to 0. And then the B, so at B point, you look at it, there are actually 0.4, look at it, 0.4 meter of pressure head from here to here. So it's 0.4. So that is 0.4 meter. For point C as well, it's the same. It's the same, 0.4 to that. So it's a 0.4 meter for C. Like I mentioned, D, we leave it next. And then you look at on the other side, G, which is sit on the water table on the other side of the well. So the G is actually 0, 0 meter pressure head. And then F is experience going down, like I mentioned, going down. Pressure, it has 0.3 meter of pressure head, the same as E, 0.3 meter pressure head. Now, we need to calculate at point D. You need to include the effect of pressure drop due to the movement of the liquid, within the media. So you're gonna have some correction factor in the calculation of pressure head. Okay, I'm gonna write a simplified, to explain further, I'm gonna write the simplified equation to find the pressure head at point D. Alright, next is how to actually calculate the point which is within the media or within the aquifer media. And here it is, we want to find D, what is the pressure head. So if you look at the diagrams, I already shrink it, but it's the same diagram. A bit changed, a bit clean up, but it's the same diagram as the previous. You see the D is actually positioned in the middle of this media, and the length of this media is 0.4 meters. So to calculate this, if you look at it, to calculate this is pressure head here. For hydraulic head at point D, you need to solve hydraulic head or hydraulic gradient value at upstream and the downstream from the point. So here is what is the value HC, what is the value HE, and then you divide it by length. So for this case, we use this formula. You look at it, we use this formula, HC minus HE divided by L. So that is how you want to determine the the head loss as the water flow at the distance 0.2 meter. I mean, here is in middle, so it is half of 0.4, which is 0.2 meter. So we calculate the gradient first. this is HC. HC, we look at what is HC. Let me check. HC, HC, it is 0.4 meter, and 0.4 meter. HE here, here is 0.3 meter. Deduct by 0.3 meter divided by the L. L here is the length of the whole media, not the length of the distance. You want to divide it the whole length because you are measuring C and you want to measure everything. Okay, then it is 0.4 meter. If you calculate this on your calculator, all these units cancel, you're gonna get 0.25. This is the gradient, and you need to actually correct your calculation of pressure head at D with this multiplication. So if you look at down here, how you want to calculate H pressure head at D, you need to actually use the point or pressure point or pressure head point of the point before it, before the HD. So here we use hydraulic head at C. So hydraulic head at C is 0.4 meter. So this is at C, not E. So 0.4 meters. You minus by, remember this one, that is the gradient loss, or gradient that is experienced, or head loss as water flow at a distance 0.25, and that is 0.25, no unit. So 0.25 times head loss as head loss rate from C to D. So you look at this, it is 0.2 meter. So it is 0.2 meter, the distance, how it traveled from that to that is how much it lost. So that we put it here, 0.2 meter. Now if you plug it, you calculate it, you will get 0.35 meter. And that is, let me put it, and that is at HP at point D, 0.35 meter. We are not done yet because the question asks you total hydraulic head. We haven't found it yet. So if you recall, HT equals to HE plus HP. So basically you just add everything. So you're gonna get the value of HP for all the points. Okay, so here for A is 0.4 meter, 0.4 meter, 0.4 meter, 0.35 meter. Let me wrap this. 0.35, and then you have 0.3 meter, 0.3 meter, and 0.3 meter. So you're done with solving the problems. Okay, example number 3. This set of example is a problem based on two-dimensional flow. The same setup, the same orientation. You have two well 1, H1, and well 2, which is H2. And then again, we're going to use the same datum point, which is we use the datum point, datum 1. So for this problem, you're asked to find there are RST, R, S, T, U, V, W, X, Y, Z. Total 9 points. So the question is you need to find all these, the pressure, the total hydraulic head at all these 6, not 6, but 9 points. And from the datum 1, yeah. And if you see here, some of the point is below the datum. Some of the point is above the datum, and some of them is on the datum. So we're gonna we're gonna solve it together. Yeah. The first thing is we need to, the same thing here, we need to find, we just put it in a table form again. We need to indicate what are the points that you need to find at point, not E, at point RST, U, V, W, X, Y, and Z. And then you need to find elevation head first. So elevation is always focusing on the datum, yeah? Elevate from the datum. So if you look at the R is actually above the datum. So it is actually 0.1 meter above the datum. So it is actually 0.1 meter. The S is sit on the datum, so it is 0 meter. The T is below, remember earlier, below the datum, the value is going to be negative. So that's going to be negative 0.1 meter. Okay, so it is actually T is below 0.1 meter below the datum line. So it is negative 0.1 meter. It's simple, and then you do the rest. For U is 0.1. Then this 0, negative 0.1, 0.1 meter, this is meter, 0 meter, and negative 0.1 meter. All right. Then next step is to find the pressure head for each of these points. You do the same thing as the previous example. Whatever that you have the point on this side, which is RST, and then UVW. Remember earlier UVW, you do exactly like how you want to find the D. It's just that just now the D is halfway through, but now it's quarter way through into the media. So you do accordingly for pressure head. So pressure head is what is experienced from the water table level. And on this side, all the 6 points will be based on this water table level. And then on this side, X, Y, Z is actually from this water table level. So you do that, and I will show you what is the value. You can actually cross-check whether the value is correct or not. So the HP for point R, HP, so it is actually, if you look at it, the pressure is going up, but not until the datum. The R is sitting there, nothing on datum. You don't confuse with the datum. For pressure head, don't confuse with datum. You just want this until to the point. So it is actually 0.3, 0.4 minus 0.1. So it is actually 0.3 meter. And R and S is 0.4 meter. And the T is going down 0.4 plus 0.1. So it is going to be 0.5 meter. So for this, again, you need to calculate using the correction or include the gradient loss due to the media, the distance to the media. And for this one, you're going to get 0.275 meter, 0.375 meter, and 0.475 meter. For this one, you got 0.2 meter, 0.3 meter, and 0.4 meter. So if you add plus HE plus HP, you're gonna get the total head. So for this one, you got 0.4, 0.4 meter, 0.5 minus 0.1, 0.4 meter. So this one, add this one, 0.375 meter, 0 and plus 0.375 meter, negative 0.1 plus 0.475 is 0.375 meter. And then this one, 0.1 plus 0.2, 0.3 meter. That is 0.3 meter, and Z is 0.3 meter. So, okay, how you want to conclude? Because you can't actually, if you answer as it is, you don't have any conclusion you need to remark something on your answer. So if you look at here, let me highlight it. R, point S, and point T, they have the same value of total hydraulic head. For point U, V, and W share the same one value, 0.375, and you can actually see the same thing as X, Y, and Z also share the same value, 0.3 meter. They are not the same, but these 3 points have the same value. So how you can conclude it is that this HT constant, total hydraulic head is HT constant, and this one HT also constant. So when HT is constant, this is called equipotential line. So in this example, you have 1, 2, 3 equipotential line. So that's how you conclude. And anything that is perpendicular means to the 90 degrees to the point that you are referring to. Here you are referring to equipotential line. So perpendicular to equipotential line, you will call this, no, it's line. You call a flow line. Okay, that settled it. Example number 4. In this question, you are asked to find the subsurface flow per meter stream using the entire flow net, given that hydraulic conductivity for this particular area is 0.01 centimeter per second. So this is the whole flow net system. You have, if you see here, you have a bird eye views where you have on the valley, it looks like a valley, right? And the center of the valley is a river stream. It's a stream which is sit on the 60 meter from sea level. So you see that when you are trying to find the flow per meter of water stream, you will need to use the equation of Q equals to K times H time NF, the number of flow channel, divided by the number of equipotential drop. Equipotential drop. So the K, you know the K is given. So K here, you get it directly. The H here is, you can calculate based on, if you look at the highest point to the lowest point of the flow. So here, H is actually 100 meter, the highest point, deduct by the lowest point, which is the stream level, and 100 plus, not 100 minus 60 is 40 meter. Done. Then the next one is, you are trying to find the number of flow channel divided by the number of drops. So the number of flow channel, where is the flow line? First of all, where is the flow line? Okay, it's easier. This is 100 meter and 90 meter is a drop. This is drop. So perpendicular to this equipotential drop is flow line. So flow line, if you look at here, this is the one, is indicated in a green line. So you have, how many flow line is there? 1, 2, 3, 4, 5 lines. But you cannot put 5 here. If you put 5, it's wrong. Here it said number of flow channel. So what is channel? Channel is actually between two flow lines. So this one channel, this one, another one, and another one. So you have 4. The number of flow channel is 4. And then you are trying to find the number of equipotential drop. It doesn't ask you equipotential line, but it is equipotential drop. You see the drop from 100 meter, 1 drop, 2 drop, 3 drop, and 4 drop. So it is 1, 2, 3, 4. So 4 drops. Then you include all in the equation. K is 0.01 centimeter per second. H is 40 meter. And then you have 4 divided by 4. Then you will get your answer as 4 times 10 minus 3. That is, if you convert centimeter into meter, you're gonna have the unit is a little bit, no, it is meter cube per centimeter meter per second meter, or it is actually like that. But the question asks per meters of stream, so that's why we have per meter of stream here. It's a little bit confusing, but we are not trying to find meter square per second, but the flow meter cube per meter of stream. So this is the answer. Okay.